Are you ready to try some more advanced things with derivatives? See how we can really use this stuff. You ready?
Yeah.
The answer's usually yes, because we're going to do it anyway, so you may as well be happy about it. 2.3. Today you're going to learn some rules. You're going to learn about the product rule and the quotient rule. Here's the scenario. Let's suppose that we start with two functions. I'm going to give you some very basic functions. F of x equals x squared. G of x equals x cubed. Here's what I want to know. Is it possible to take the derivative of one function times another function? Notice how this is f of x and this is g of x, right? The question is this. The question is, this equal to this? I need more room. I want you to really write that down and contemplate it. Is that true? Question is, can I do it? Can I break up derivatives by multiplication? Can I break up derivatives by multiplication? Can I say, oh, the derivative of f of x times g of x is the same as the derivative of f of x times the derivative of g of x? Can I do that? I don't know. We have no idea. I mean, I'm just asking you right now. But I can tell you this. If we can find one example where it's not true, then this whole scenario falls apart. So what we're going to look at is, let's look at this example and see if it's true for this. Now, I'll tell you right away that you could get x to the fifth right there, couldn't you? So we know for sure that this is true. This is the same as d dx of x to the fifth. What's the derivative of x to the fifth, ladies and gentlemen? So we know for sure that this is supposed to end with 5x to the fourth. Do you believe me? Yes, no? Okay. Okay. Let's try this way. Let's try to do it. The derivative of the first times the derivative of the second. What's the derivative of x squared, our first? What's the derivative of our second? Is it the same? We get 6x cubed. Okay, we got two different answers. Which one is right? 5x to the fourth or 6x to the third? Which one's right? You should know. You should know right now which one is right. Which one is right? This one? This one. Which one's right? Is this for sure equal to x to the fifth? Every time. Every time. Do you know how to take the derivative of x to the fifth? Every time. We know for sure that this way was right. What I'm trying to say is, do you end with the same thing? I know for sure, guys, for sure, this is the right way. It gives me a correct answer. The correct answer is 5x to the fourth. That's the correct answer. Is this the correct answer then? No. So does this way work? So, can I separate derivatives by multiplication? No. Is this true? No. No bueno. No, you can't do that one. That's not true. You can't separate derivatives by multiplication. So, what are we supposed to do when we get these functions that are multiplied together? We either have to distribute them, Or we have to find a better way, and that way is called the product rule, which is the name of our section here. We're going to look right now at how we actually do the product rule. So, product rule. Product rule says, well, if this doesn't work, what is the correct way? What do you do if you have one function times another function? You're trying to find the derivative of those things. Well, here's what you do. This is our rule. If you want the proof of this, come and see me. I'll give it to you. It's a little bit too long for our class. I usually will prove the things, but I'm not going to prove the quotient rule or the product rule for you. If you want to see it, just come and see me, okay? So the product rule says, here's how we're going to go about taking the derivative of a product. We're going to take the derivative of the first one, the first function, times the derivative of the second function. I'm sorry, the derivative of the first one times the second function, plus the first function times the derivative of the second function. I'll write that out in symbols so you see it. You take the derivative of the first function times the second one. You leave the second one alone. You add to it the first function, left alone, times the derivative of the second. You've still taken the derivative of each one, but it's different than this. You have that addition in there, that product. I like to think product plus. P goes with P, product plus. So we're going to have that. You're going to see in the quotient rule that we're going to have a minus sign in between there. So product plus. Associate the product with a plus. By the way, would it work for over here? Let's check real quick just to verify, okay? So d dx of x squared times x cubed. Again, we're supposed to end with 5x to the fourth, right? That's what we're supposed to end with. If we do this, here's what it says. Watch what the product rule says to do. It says you take the derivative of your first function, that would be x squared. You find the derivative of your first function times the second function. That's how to write that out. It says you find the derivative of your first function times your second. Are you okay with the notation? Derivative of your first function times your second function. Then you have a plus sign. Then you write your first function times the derivative of your second function. In English it says derivative of the first times the second plus the first times the derivative of the second. Let's see if it works. What's the derivative of x squared? So this becomes 2x. Oh, ladies and gentlemen, do I need to take the derivative of x cubed in this case right here? You follow the d dx. That's why I like the d dx. It says this is what you're taking the derivative of. That's why we're going to write it like that in this class. Go, oh, this says take the derivative of this one, but don't take the derivative of this one. You're only taking the derivative of whatever's inside your brackets there. Do you see it? That's why we use that. It says, oh yeah, okay, derivative of x squared, that's 2x, times x cubed, plus, do I take the derivative of this x squared? How about this x cubed? Yeah. Yes, that's why I said d dx. It says take the derivative of that. That's 3x squared. If we make this a little prettier, we have 2x to the fourth plus 3x to the fourth. That gives us, hey, are we right? Yeah, that works in that case. That's not a proof. That says it works for that example. You have to be able to prove it works for every example. See me for that if you want to.
Or we can just trust it works for everyone.
You can trust it. Yeah, you can trust it if you want. I would. I mean, it does. So save me some time. But so in English, the derivative of the first times the second plus the first times the derivative of the second. If you want to write that down, you can write that down if you like it at your leisure, or just watch the video again and hear me say it like 40 times. Just press rewind, okay? Derivative of the first times the second plus the first times the derivative of the second. How many will feel okay with that so far? Now, we're going to do one example on how to actually do this. I'll show you why it can be useful a little bit later on, how it really, really does help us out a ton, and why we need it. For right now, you're going to be wondering, well, why can't we just distribute all the time? For right now, we will be able to distribute all the time and get the same exact answer. I'll prove it to you right now. I'll show you. However, later on, you won't be able to do that. And so the product rule will become very, very important for us later. For right now, it's going to seem like, well, wait, hang on. Let me show you an example of this. Hey, look at my function. Do I have a product? Do I have one function times another function? Sure, absolutely I do. I've got this function in parentheses times this other function. But do you see that I could distribute this? Do you see it? If I FOILed this all out, I could do the derivative that way. I could do it for sure. I could do that. And so you might be wondering, why do we need this at all if I can always distribute? And the answer is, well, you can't. You can't. Or you probably don't want to. For instance, what if I gave you, now we're not there yet, I'm jumping ahead to give you a precursor to what we're going to be doing later. But here's why we need the product rule, okay? You with me on this? We're not going to do it now, I haven't showed you this yet. But what if this was to the fourth? Okay, do you want to distribute that 4 times and then distribute that one?
Not really.
Heck no. No, that's ridiculous, okay? That'd be crazy. That'd take up more time than limits would do, all right? No, we don't want to do that. We want to find ways around that. The product rule is the way around that. Do you understand? That's the idea.
So it'd be good practice to start using the product rule now instead of...
Yes, absolutely. It's gonna, on your homework, it's going to ask you to do both. Do this 2 ways. And I'm going to show you next time how to do this 2 ways. I'll leave you with one. Don't pack up yet. I'll leave you with one more thing. But it says, distribute this, find the derivative. Then use the product rule, distribute it, and then you're going to find out that you have the same exact thing, okay? So you're verifying that this product rule does work and distribution does work. You get the same exact thing. That's what kind of this idea was about as well. One last question. So a lot of people always ask me, so I'm answering right now in the last couple minutes. Well, hey Leonard, isn't this a product? 3x squared, isn't that a product? Well, of course it is. It's 3 times x squared. Yes. Why don't we use the product rule for this? If it's a product, why don't we use the product rule? Wouldn't it come out different? And the answer is, we kind of do use the product rule, but we cheat a little. Well, we don't cheat. We just don't show a part of it. Here's why. If you consider this to be a product, check this out. You'd have the derivative. This would be your first, and that would be your second, true? You'd have the derivative of your first times your second plus your first times your derivative of your second. All right, very good. What's the derivative of 3? 0 times x squared. That's going to happen every time because that's a constant. So if you consider that to be a product rule, the constant is always going to go to 0. So we really don't show that step, do we? We just show, oh, look at, hey, the 3's outside. That's why we can pull the 3 outside of our derivative. That's a constant. We can do that. It's product rule. It says, here's positive plus 3 times the derivative. That's 2x. That's 6x. That's why we can do that. Okay, so to answer any questions you might have in your head, why don't we have to use the product rule? You really are. You're not showing. We're going to start with that problem next time. So we're working on our problem. I'm going to show you that with the product rule, yes, there are other ways to do it, but ultimately we need the product rule because I think I showed you last time that we're going to have that if we have any sort of exponent here or here, we're going to need it because you certainly don't want to distribute that out 30 times if that's your exponent. That would be crazy. So how do we do this 2 ways? Well, way number 1 is, what if we don't even consider it to be a product at the very end? What if we distribute those parentheses and make it so we just have a basic polynomial in this case? Well, if we do that, we'll get 3x to the 6th plus 2x to the 3rd minus 3x to the 4th minus 2x. Are you okay with that so far? Check for any like terms. Do I have any like terms? So maybe reorganize it just a little bit because that's the way we like to see our polynomials. And then the question is, can you take a derivative of that thing right there? Yeah, that. That's actually pretty easy. So if we do dy dx, what's the derivative of this polynomial? Can y'all tell me real quick? Thank you, all of you. Appreciate it. Let's all try this. What's the derivative of 3x to the 6th?
18x to the third.
Okay, minus what?
12x to the third.
Then?
6x squared.
Uh-huh.
Minus 2.
Is that it? Okay, so that's our derivative. Now, the product rule should give us the same thing. And again, we're practicing the product rule in case I give you something like that, where you can't just distribute it. You'd have to distribute this one and then distribute. That would be very annoying. So we're going to verify with a couple of these examples that, yeah, you are going to get the same thing if you use the product rule. Do you remember what the product rule said to do?
Derivative of the first one.
First one?
Times the second one.
Sure.
Add the derivative of the second one plus the first one.
Yeah, that's very good. So there, I think the book has it in a slightly different order, but because of the commutativity of addition and multiplication, it really doesn't matter. As long as you take the derivative of one times the other, plus the other one times the derivative, like the derivative of the first times the second, plus the first times the derivative of the second. Or any way you kind of permute that, that's fine. Take the derivative of one of them times the other, then multiply times that one times the derivative of the other. In other words, for us, we'd say the derivative of the first function times the second function. So that's our separation of the product there. Plus the first function times the derivative of the second. So derivative of the first times the second plus the first times the derivative of the second. That's how we like to say that. That's like how we like to see that. Are you guys okay on how this is coming about? Again, we can't just take the derivative of this and this and this and this. That doesn't work. Anytime we have a product there, we have to use a product rule, or we have to distribute and do it term by term. So far, so good? Can y'all tell me what's the derivative of x squared minus 1? What are we going to get out of that?
2x.
So this will be our 2x times 3x to the 4th plus 2x. Plus, do we take the derivative of this? This piece right here, folks? No. Okay, so x squared minus 1.
We do
Derivative of this, can you take the derivative of that?
yeah. 12x to the third
12x to the 3rd, okay.
plus 2.
Plus 2, cool. Notice how you follow the ddx. That ddx tells you what you're taking the derivative of. It says the ddx of this, yeah, but not that one. Not this one, but yes, this one. So follow the ddx, you'll say take the derivative of this little piece. If you can do that for these rules, it will really, really help you out. Raise your hand if you feel okay getting down that far. Now, is this the same as that?
Not yet.
If we distribute it, it should be though. Let's find out. Here we'll get our 6x to the 5th plus 4x squared plus, we're going to have to FOIL that, right?
Okay.
Don't worry, we're not done. We're like, wait a second. Oh no. Oh no.
No.
Just wait. Just wait. If we FOIL this, distribute it, we're going to get 12x to the 5th plus 2x squared minus 12x cubed minus 2. Well, at least I see the minus 2. That's fine. You guys okay with the distribution? Just some basic algebra here. Now, if we do combine some like terms, I see a 18x to the 5th. Cool. I see a 12x to the 3rd, minus 12x to the 3rd. Gotcha. I see a 6x squared. I have minus 2. Got a minus 2.
Now, say we wanted to find the second or third derivative, can we just use that polynomial from that point?
Oh, sure, yeah. Find the second one. Bam. Just look at these are the same derivative, right?
Right.
It is the same. This is just a different way to go about it. Of course, you, like I said before, Could you distribute that and do it this way? Absolutely. For this one, that might be the easier way to go about it. It's a product rule with just one parenthesis, but as soon as you have some exponents, everything changes. And you definitely don't want to do this if there's some exponents associated. So keep in mind, we're building up to things, okay? We're not there yet, we're building up to things. I'm giving you kind of like the groundwork for the stuff we're doing later. So yeah, you need to understand the product rule before we get to something that's called the chain rule. Because then you're going to be using the product rule in combination with that thing, and in combination with the quotient rule, and in combination with these other ideas. So you do have to understand it, but I'm showing you right now that they are the same. It's just a different way to go about it. Do you guys understand the idea there? Also, have you read through the book, The Proof of this? The proof's in there. It's actually not a hard proof. There's just one little thing that they do. They add on an expression that equals 0 so they can factor it, and you can prove that the product rule works really well. Really easily with that. So read through that if you haven't done that already. That's in this section. Read through the proof of the product rule and the quotient rule. It's not too hard to follow. I promise it's not too bad. Read through that. Would you like to try a couple more? Let's do one more with the product rule. I'll give you an example of how some of the problems in your book are going to look. That way you can kind of have a bearing to go forward with that. Then we'll talk about the quotient rule, and that'll wrap up our day today. So, the last example of just a straightforward product rule. It's not too bad. All it is you have to remember what this does. A derivative of the first times the second plus the first times the derivative of the second. Remember that. Be able to identify what products are, and then you're good to go. By the way, did I show you last time why we don't have to use the product rule for something like this? Just that term? Even though it's being multiplied, did I show you that?
Yeah.
Okay, cool. Because when you do the product rule with that, the derivative of the constant goes to 0, and that piece falls out of the expression. Okay. Well, let's do that. 1 plus x squared, and then x squared. Firstly, you need to be able to see that this is in fact a product. Do you see it's a product? What we mean by a product is not just like this, okay? This wouldn't be considered a product rule. Explain the difference between something like this and something like this. When I say product rule, I don't mean what's different between here and here. What is it?
Constants in front of it.
The constant, okay, even this wouldn't be a product rule.
Exponents.
Not exponents. Not just exponents.
Grouped terms.
Though these are group terms.
You have two different groups of terms with the square root.
Okay, different terms that involve what? Constants or variables? Okay, product rule means we're multiplying variables. Okay, expressions that have variables in them. So this, do you need a product rule for that? No. No. That's just a constant. You could actually pull that outside of your whole derivative. The derivative of this thing is going to be 1 times 3. That's what it's going to be. Okay, derivative of x is 1, derivative of 2 is 0, 1 times 3 would be 3. That would be the derivative. Right? So you get that even if you distributed the 3, that'd be fine. So we're not talking about products of constants times things. We're talking about products of functions in terms of x times functions in terms of x. Are you with me on this? Which is why we don't have to use the product rule when you find the derivative of that piece. That's just a constant times something. We're talking about functions of x times functions of x. You need to see the difference. Are you okay on the difference in that? You sure? So do we have a function in terms of x times a function in terms of x on that problem up there? Yeah, in fact, this is it right there. Let me erase that 3. We don't need that. Let's go ahead and let's try to set up the product rule. Now, could you distribute it and do the work that way? Of course. Yeah, of course you could. You could distribute this to be square root of x plus x squared square root of x. You would have to combine some exponents there, but then you could take a derivative. Not too bad. Maybe I'll show you that in just a minute. If we do the product rule, however, why don't you guys figure out how to write out the product rule? Set up the d dx of the first expression times the second, plus the first expression times d dx of the second. I want to see that on your paper. I want to see the work. I don't want to see just the answer, okay? At this point, you're learning this stuff. So I want to see every step. I want to see it written out just the way I've showed you. So derivative of the first times the second plus the first times the derivative of the second. After that, the calculus is done. Then you just got to do some algebra. So first I want to see if you have it set up right. Let's see. Check your paper. What you should have is the derivative of the first times the second function in terms of x. Do you guys all have that? Okay. Then we have what? A plus or a minus between them? It's always a plus. Plus product. Product plus. Plus what comes next? Do I need parentheses around that? I've told you how important parentheses are for this, right? Parentheses being multiplied by something, that's important stuff. So have that times the derivative of the second expression. Show of hands, how many people made it that far? Great. If you made it that far, you understand the product rule. It's the derivative of the first times the second plus the first times the derivative of the second. We have that down. Now we just have to follow the ddx. The ddx is the calculus for us, right? That's the derivative at this point. So if you just follow that little piece, take a derivative piece by piece, you'll have the right answer. So understanding product rule, great. Then just do the ddx, okay. They're all going to be kind of basic derivatives that we've seen before. It's just applying them together within the context of a quotient or rule, or a product rule, or we'll find out later a chain rule. Derivative of 1 plus x squared. What does this give you, please? Great. Derivative of 1 is 0. Derivative of x squared is 2x times the square root of x. Plus, do I take the derivative of this? No. Okay, so 1 plus x squared, I'll leave it in parentheses, times, oh, derivative of the square root of x. Might want to change that, huh? So if we did, I'll write the extra step so you can see it. We do, yeah, x to the 1/2. If we take that derivative, that's 1/2 x to the negative 1/2. Did you get 1/2 x to the negative 1/2? Mm-hmm. Cool deal, all right, very good. Now making it maybe just a little bit prettier, 2x root x, you could combine those with fractional exponents if you wanted to. What's on the denominator of this expression? On the denominator of this expression. On the denominator. There's a 2. There's for sure a 2 because of that 1/2. Do you see the 2? What else? Root x, because x to the negative 1, that says denominator, and then the 1/2 says it's a square root. One plus x squared is on the numerator. Unless we want to get fancy and break that stuff up, find common denominators, we're just about done with that problem. How many people feel okay with this one?
Can we convert the square roots to fractions and then solve that?
Sure, we can do that as well. You'd have to distribute, from here you'd probably distribute that. You'd have 1/2 x to the negative 1/2 here, and you'd have plus 1/2 x to the 3/2.
And then you would combine that with your other, if you use fractions over there, because you've got 2
yeah, we could do that. We could try that. So this is 2x to, let's see, 1 plus 1/2 is 3/2. Plus, if we distribute, you'll get 1/2 x to the negative 1/2 plus 1/2 x to the 3/2. And we're getting that because, of course, when you multiply those exponents, you add them. You add those exponents together. That's the 3/2 for you. So I've just distributed and distributed. 1/2 x to the negative 1/2, and then 1/2, the x squared and the x to the negative 1/2 gives you x to the 3/2. You all right with that? Then sure, you could combine these as well.
You'd end up with like 5 halves over x to the 3/2.
Yeah, 5/2 x to the 3/2 plus 1/2 x to the negative 1/2. If you wanted to leave it in terms of exponents, that's probably what you would end up with, is those exponents just like that.
And that's an acceptable way?
That's actually exactly what you'd get if you distributed this and then took the derivative. If you, just do it in your head if you want to. Think about it. If you distribute this, you're going to get root x, right? Square root of x, the derivative of that is this right there. You see it? The derivative of this is this one. You follow? Distribute this, this is going to be x to the 5 halves. You see the 5 halves out of that? X to the 5...
1/2 plus 2.
X to the 1/2 plus x to the 5 halves. That's what that is distributed. If you can't get that, do it later on your own. Distribute that and figure out those exponents. This derivative is that piece right there. The piece of this derivative is 5 halves x to 3 halves. It's right there. It's the same thing. Same exact thing. Feel okay with this so far? All right, cool. Let me show you one more, and this really illustrates the idea of the product rule. And see if you can do it in general. Kind of a fun little problem, almost like a little puzzle. Not a hard puzzle, don't worry. This one time my parents, I love my parents to death, but they gave me this one puzzle. It was, have you ever done a puzzle that doesn't have straight edges? Very difficult. It was shaped like a butterfly, right? And instead of having like normal butterfly, it was like a psychedelic butterfly, like, what do you call it stuff? What is it?
Tie-dye?
Yeah, it was a tie-dye butterfly with non-straight edges and a non-straight outline. I spent at least 18 hours doing it and then ended up burning in a fireplace. It's so ridiculous to me. So it's not a puzzle like that, okay? This is like one of those 4-piece jigsaw puzzles you get in like 3rd grade, okay? Or no, maybe kindergarten. Puzzles, okay? You got it. Fun.
It's not like a double-sided puzzle.
It's not a double-sided puzzle.
That's not fun either. 2 different pictures on different picture on each side.
Oh man, that'd be ridiculous. Not one of those either. No, it's this puzzle. You see, before, you could have gotten around this problem without doing the product rule. You could have gotten around this problem. This one, well, you might still be able to do that. However, it's going to be a little bit easier if you do the product rule with it. The idea is, what if you have this, and I tell you only 2 things about it? I say f of 2 is 3. F prime of 2 is -1. And I say find g prime of 2. That's my goal. Okay, well, it's not too bad. What we're going to have to do, though, is figure out some pieces to fill in. We want to find the first derivative of g, and then fill in the 2. Do you follow me on this? So let's go ahead, let's use the product rule. Firstly, do you see why we need the product rule here? Do you see it? Do you see why? Do you have a function in terms of x times a function in terms of x? This is a function of x, yes? This is another function of x, and they're being multiplied. That's definitely the product rule. So what I'd like you to do, just follow the product rule with this. Go ahead and do that now. Follow the product rule. I want you to find g prime of x. Derivative of the first times the second, plus the first times the derivative of the second. Just write it out. Derivative of the first times the second. Yes? Plus. The first times the derivative of the second. If you want to use d dx, you can. Would you agree that that is, in fact, the product rule for this problem? Derivative of the first, yep, times the second, okay, plus the first, got it, times the derivative of the second. I don't care that the function's not listed. It's f of x, so whatever that happens to be, that's what would go here, and that's what would go here, just like in our other examples. You with me on that? Well, let's do the derivative where we can. Give me the derivative of x squared plus 1. So this is 2x times f of x. True? Plus, do you take the derivative of that? X squared plus 1 still needs to be in parentheses, ladies and gentlemen, times, what's the derivative of f of x? Aha, f prime of x is how you write that. We don't have the actual function, but you know that f prime of x stands for the derivative of f of x. Do you see that? Okay, cool. Now this, would you agree, is g prime of x? That's the derivative of g. That's what that is. What we want to find out is g prime of 2. What does g prime of 2 tell you to do? Everywhere you see x, plug in 2. Everywhere you see x, plug in 2. Everywhere. So for us that means, tell me what I should have. 2 times 2, great, because x is 2, fantastic. Times f of what?
2.
That's everywhere you see the x, correct?
Yeah.
Okay. F of 2. Plus, in the parentheses, tell me what else I got. Times f prime of what? Sure. Hey, what happened to all the x's? They became 2's. This x became 2, therefore every other x became a 2. Raise your hand if you feel like that so far. So it's kind of just a little exercise so you get used to the product rule and then filling out the numbers with the substitution. Let's go just a little bit further. There's no more x's. We can now make some substitutions. I know that this is 2 times 2, so that is 4 times, hey, what is f of 2? Have I given you that information?
3.
4 times 3. Plus this is all 5. 5 times, what's f prime of 2? Cool. Is it possible? Sure, yeah. They have to give you this though. They have to tell you what that is. I wouldn't be able to do this without that specific information. So all together we're going to get
7.
Cool. 7. Ah, super fun. See, puzzle. I told you you'd enjoy it. Puzzling, why I find that interesting, but what did we just find? G prime of 2. Yes, that's exactly what we did find. What's it represent? Slope of this curve at that x value. So what you just found, this is actually a slope. The slope would be 7 of that curve, whatever it is, at x equals 2. Do you see that? Kind of neat. We're finding slope. Always keep that in mind. What you're doing is you're finding slope and you're finding derivative.
And we still don't know what f of x is.
Nope. No, you might be able to figure it out. Or at least something that represents it, but no, we don't know. Hey, ladies and gentlemen, are you okay with the product rule? In general, it's really not that hard of a rule. If you have this down, that's it. It lets you break up a problem without doing distribution so that you can do it piece by piece, and that's the idea. Now we're going to look at the quotient rule. Quotient rule is just slightly more involved, but it's not that hard either. It's just a product. It's very similar to the product rule. Same idea. You ready to see it?
Yes.
The proof, again, is in your book. It's not hard to follow. Go ahead and just look at that when you get home tonight. Okay, so quotient rule. Quotient rule asks this question. It says, can you take a derivative of a quotient? Something in terms of x over something in terms of x. That's what this question is asking. And the idea is, well, can I just take the derivative of f and divide by the derivative of g? Do you think that's going to work? No, that never works. We can't separate derivatives by multiplication unless you use the product rule. We can't separate derivatives by division unless you use the quotient rule. Are you with me on that? You can't just take a derivative of the top and the bottom. That's never going to work for you. I give you a very simple example about how that's never going to work for you. If you did that, you'd get something over 0, true? Yet we know that this would be the same thing as 1/3 x squared minus 1/3. True? Derivative would be very easy there. 2/3 x, and that's it. So We can't just take the derivative of the numerator and the derivative of the denominator. That doesn't work for us. We have to have some other way to do it. By the way, you probably wouldn't, you could, but you probably wouldn't want to use a quotient rule for this very simple example. You'd probably break it up, just like I did here, and then you take a very easy derivative. The quotient rule and the product rule are really meant for some more extensive ideas, things where you don't have other ways to do it. That's really the benefit of these rules. So I'll show you what the quotient rule says. Quotient rule says, okay, in order to take the derivative of a quotient, we're going to take some derivatives of each piece, but we're going to put them together in a unique way, just like we do with the product rule. It says you're going to take the bottom function times the derivative of the top function. I'm going to use some logic that's not quite mathematical, but it's going to make you remember something. Product meant plus, right? P with P. Product meant plus. What's the opposite of a product?
Minus.
A quotient. What's the opposite of a plus?
A minus.
So what are we going to use here, a plus or a minus?
Minus.
Okay, it's not very mathematical, but that's the way you remember it, okay? Product with plus. Quotient, I think quotient has a straight line, so quotient has another straight line. Quotient minus, that's how I remember it. Actually, I remember it because I've done this so many times, I can't forget it. It's stuck in my head like jingle bells. I have a song for that too. The math song for Jingle Bells. Just watch my videos, you'll see it. Quadratic formula song, that's right. So the low function times the derivative of the high function minus the, what would I do? High function times the derivative of the low function all over squared. Or if you prefer, if you like the DDX format like I do, this says the same thing. That says the same thing. Oh, there is. There is, and you know what? I think I liked it, so I'm going to steal it from Michael. So he introduced it. Actually, I've heard it before, but it's a good. It said, what's it say again?
Low D high minus high D low, square the bottom, and away we go.
That's right. Very cool. Low D high minus high D low, square the bottom, and away we go. But you have to do this with it. Otherwise it's that's a Harry Potter version of this math. Yeah. Low D high minus high D low, square the bottom, and away you go. Yeah. Derivative of the bottom, derivative of the top times the bottom, or the bottom times the derivative of the top, minus the top times the derivative of the bottom all over the bottom squared. That's really what you're doing. Low D high minus high D low, square the bottom, away you go. Sound good?
Is the first one supposed to be the bottom, or can it be the top first? Yeah.
Hang on.
Can you do that?
You mean, can you interchange these two?
No, the start, from left with the minus sign, right.
Can you interchange these two?
Yeah.
Absolutely not.
Okay.
Because subtraction is not commutative like addition is. Okay, if you interchange those, is 5 minus 7 the same as 7 minus 3? I'm sorry, that's not even close to the same thing. Is 5 minus 7 the same thing as 7? No. So if I just interchange, you're like, wait a second, no, that's not even close. If I interchange these two things, no, they're still not the same. You can't take the top times the derivative of the bottom minus the bottom times the derivative of the top. That's what you're asking. You could interchange these. The derivative of the top times the bottom. Multiplication is commutative. That would be fine. Subtraction is not. So this is order dependent. Okay, you have to do it. That's not true with product rule, is it? That one, it doesn't really matter. But this one very much so matters. That's why I like the mnemonic. Low D high minus high D low, square the bottom. What do you got? You got it? Shall we practice it? I think so.
Oh, I thought you were going to recite it today.
No. That's that. I'm not going to make you sing.
It's not a requirement of this course.
So you made us do in high school.
I did. This is no longer high school. We graduated singing. Now, let's look at an example. These are slightly different than the product rule because some of these examples can't be done without the quotient rule at all. You'll see it. By the way, you're going to find that the taking of the derivatives really isn't all that hard. I mean, you know pretty much everything there is to know at this point about taking simple derivatives, right? Move the exponent to the front, you take one away from it. That's a derivative of basic functions. Now it's just using the rules to split these up into little pieces to make them easier. So if you know the rules and the derivative, hey, you're good, you're fine, you're good to go. It's like you squared the bottom, away you go. Anyway. Now, this problem is slightly different than if I would have given you this. Look at the boards, notice the difference. If I give you that, there's something you can do with that.
Separate.
Yeah, that's separable. You can separate into 3 different fractions, simplify those exponents, then take the derivative of every single one. That actually might be the way to go for this problem. You with me? That'd probably be easier than using all this stuff, the quotient rule. Separate 3 fractions. I think some of your homework was like that, wasn't it? Separate it, simplify the fractions into, so combine exponents, and then take a derivative of each little piece, and that's fine. However, as soon as you do this, can you do that anymore? Well, you can. You can separate 3 fractions, but it's not simplifiable like you did before. You can't say x cubed over 2x plus 5 is one term. You can't do that anymore. You can't separate this 2x plus the 5. You can't do that. You see what I'm talking about there? Now there might be a way if you multiply by the conjugate. No, still even that, it'd make it worse. Nothing good can come of this. The only thing we can do is understand that, hey, that is in fact a quotient, right? Does it fall into the category of the quotient rule? Which means I have a function in terms of x over a function in terms of x. Do I? I wouldn't want to do it for this. That's not a function in terms of x, that would just be 2. That, in that case, separate them. Man, that's so much easier. Don't use the quotient rule for stuff that you can do other things with. Usually, the other things are easier. So, let's try to set up the quotient rule. Why don't you do it? You know what? I'll do it with you the first one. I'll give you one in just a second to set it up, because I want to show you how exactly I want it. For dy dx, that would be the derivative of y with respect to x. We're going to take low d high minus high d low all over the bottom squared, and then away we go, whatever that says. We're going to do that. But I do want to see your work. I'll give you a partial credit if I see that you know how to do the quotient rule, okay, which means I want to see every little step. You're learning this right now, and if I see wrong answers at the end, I want to see where your mistakes happened. So I want to see all this work. Understand? I want to see it. So we take the g of x, in that case, this is the bottom function, the 2x plus 5. The low, the d, the high. Low d high minus the high, what's our high again? And then the d low, something like c low. You guys watch The Voice? Great show, by the way.
You get so sidetracked.
Yeah, some student earlier said, "Do you have ADD?" I'm like, I don't know. Look at that butterfly. That's funny. Over the low squared, the bottom squared. So we have, you don't need brackets, you use parentheses if you want. Low, d high, minus high, d low, square the bottom, and you're done. Doesn't quite have the same. How many people can follow that though? Rich can. Right for that. Notice how we've changed this quotient into something. Well, these are very easy derivatives. Very easy. You just have to follow the rule to make sure you get it to easy derivatives. Everything is pretty much going to be like that. Memorize the derivatives, know how to do the derivatives, memorize the rules, and put them together. That's it. Nothing's too extraordinary. You know, just follow the rules that I give you and you'll be fine. I know I make it sound very easy right now, okay? Some of the rules, yeah, you have to really know how they interplay. I'll show you that as we get going, but if you understand the rules really well, the class becomes kind of a piece of cake after that. Does the 2x plus 5 change? Does the x cubed minus 3x squared minus 5 change? Follow the ddx, follow the derivative. Everybody, what is the derivative of this, please?
3x squared minus 6x.
So far, so good? I don't want to see this garbage from you guys anymore. You leave that, I'm marking off points from you. Why? You absolutely must have parentheses. You're going to be distributing that in just a second. Okay, so you must have parentheses there. You leave me just this, I'm going to go, no, you don't understand what you're doing. That's different than this. So show me the parentheses where they're applicable. Does this change?
No.
There's no ddx associated with that. So x cubed minus 3x squared minus 5, okay. Does this change?
Yep.
What is that?
2.
Now, I don't need parentheses around the 2. Okay, that's just one factor. That's all right. But the other things, yeah, you got to have those. All over, well, we're going to have the 2x plus 5, and we're going to have it squared. Rarely will you distribute this. Rarely will you distribute this. This one, yes. We'll distribute this and we'll combine them. Rarely will you distribute that. And the reason is, if you can simplify it, you will. You'll try to simplify that thing. And it's already factored for you very nicely. Okay, you don't want to get the 4x squared whatever. Not plus 25, but you get 4x squared plus 20x plus 25. That's what you get. You don't really need to do that. Just leave it the way it is. This works out for us very nicely, especially when we start graphing these, which, hint, hint, you're going to graph those without a calculator. It's fun. Like another puzzle. Double-sided butterfly with psychedelic colors. It's that type of puzzle. But it's still kind of fun. So not a throw in the fireplace type of puzzle. It's a fun puzzle. We'll talk about how to do that, and this form fits a little bit better for us. So we'll continue. Let's go ahead and distribute this. Can you tell me what you get when you distribute? Okay. I actually heard none of you. I'm just doing this in my head. Thanks a lot, guys. Appreciate it. That's okay. I know you know how to distribute. I'm going to do both these at the same time, the negative and the 2. So minus 2x cubed plus 6x squared plus 10. Do you see where the plus 6x squared and the plus 10 are coming from? Yeah. Okay, good. Maybe little combine like terms here. If we combine some like terms, I'm seeing the x cubes. That gives me that 4x cubed. Awesome. Oh, I got a whole bunch of x squareds going on, don't I? By the way, if I'm making a mistake, you let me know. I get, see, a 12, negative 12, positive 15, positive 6. That looks like it's going to be 9? Oh, doubled that one. Minus 30x. That's your derivative. What did we just find? What's this? What's that stand for? That's derivative. What's the derivative stand for? Slope of that curve at what point? Whatever I want. So if I asked you to find the slope at x equals 1, could you do it? Sure, you'd plug 1 into here to find the point, 1 comma something. True? Then you plug 1 into here to find the slope. You'd have a slope and a point. Y minus y1 equals mx minus x1. You can find the slope of that tangent line to that curve at that point. So this is still a slope formula. Now what you would do in general, you'd try to factor this and simplify it if you can. You can still do that. Sometimes that will help you. Now, when you have like an x cubed, don't really worry about that so much. Those are fairly difficult to factor in general. If you can, try it. See what you can do. Could you take a second derivative of that? You see, you'd have to have another quotient rule. However, I haven't showed you how to deal with that exponent yet. So when you did low d high minus high d low, that d low would be the derivative of 2x plus 5 squared, right? So you'd have to distribute that at this point, or use a product rule within that at this point. Yes, you can use rules within rules. We're going to have a lot of that in this class. For instance, if I do a problem like this one, I'm not going to do this for you, I just want to give you a heads up. If I ask you to find the derivative of that, do you see how firstly there is a product rule? Function of x times a function of x. That's a product rule. Then when you go through that, as you're doing that, that's the first thing you see. From the outside in, you see a product rule, right? As you're going through the product rule, it would be derivative of the first, that'd be fine, times the second, still okay, plus the first, all right, times the derivative of the second. And as soon as you get to the derivative of the second, how do you take the derivative of that thing? It's a quotient rule. You would have a quotient rule that is within the product rule. See that? So we're going to talk a lot about this, how the rules will have an interplay, which ones you do first and which ones you do second. Basically, if you can follow the ddx, follow the first rule, then follow the ddx. And wherever you have a quotient, then you use quotient rule, or then use the product rule. We'll get there. Probably get there right now. Let's try one.
That wasn't much of a segue. You know, I thought we had.
That wasn't my segue. It was a 2-second segue. Come on. That's good for me. I have ADD, apparently. I actually have the opposite of ADD. I focus only on math and other things.
Lady Gaga.
Good news.
Strange.
All right. Now, we're going to do this the hard way. We're going to do the hard way because I want you to see it. But there is an easier way to do this. The easier way to do this would probably be to distribute this, combine like terms, and then use one quotient rule, right? But I want you to see how the product rule will play in this. Because if I do one thing, you can't do it anymore. If I gave you like a 5, well, you definitely wouldn't be distributing that anymore, right? So you better learn the other way, because I'm certainly going to give you something like that. You're going to need to be able to do it. So we're going to learn how to associate the product rule with the quotient rule and use a rule within a rule right here. Now, when you look at the first rule to use, you got to see which one's overlying, encompassing more of the problem, the product rule or the quotient rule. The quotient rule clearly is. It says the product is actually within that quotient. Do you see it? So the first rule we're going to use is quotient rule. Let's write out the quotient rule. What is it again? Low D high. Low. What says my low?
X squared minus.
Do I do anything to the low right now? Low. Then what?
D high.
D high. So we're going to do D high. Oh, nasty. Low D high. And then what?
Minus high.
Minus. Okay, like the minus. Low D high minus the high. Okay. Real quick, I want you to look at the board here real quick. Make sure that when you distribute this, you still have a bracket. If you distribute, you still have a bracket, because that negative will ultimately change those signs. You see what I'm talking about? That's important. So you wouldn't distribute the negative now. You distribute all this and then do the negative lastly. But you need a big old bracket around that thing. High and then D, low. All over what, ladies and gentlemen?
Low square.
You're saying the bracket will go from the high and the derivative of the second? Yeah, okay.
Yeah. That thing like that. Because you distribute all that, and then the negative would go. Okay?
Now, can you just stop and like do a sidebar and then do your product rule for your?
Well, we're gonna do this right now. So, but I need you to understand that this certainly is the quotient rule for us. Are you okay with that? That is the quotient rule. Now you follow your ddx. Don't change anything much at all. This isn't going to change. X squared plus 2 squared, sure. This isn't going to change except for that derivative, 3x minus 1, x squared plus 4, and that would give you a times 2x. Are you okay on that ddx? This is the rough one. Do you see what this does to you? So you'd say this is fine, x squared plus 2. Okie dokie, got that. Then you follow your ddx and go, I don't have to take the derivative of this, I do have to take the derivative of this. And as soon as you do that, do you see how that's like a problem within a problem? That is a product rule. Product rule says derivative of the first times the second plus the first times the derivative of the second. You'd get that. This one, well, we didn't change that at all. This one, we followed the ddx and just got the 2x. So I'll do this very quickly so you just get the answer that I'm looking for. The derivative of the first times the second plus the first times the derivative of the second that would be your problem. Do you see how, well, I did it really quickly. You would show your work off to the side and I should do the product rule. This is 3x squared plus 4 plus x squared, I'm sorry, 2x, the derivative of that is 2x, 3x minus 1. That's that little piece right there. So that's the product rule. After that, if you wanted to spend, I'd be impressed if you got down to this far, okay? That'd be fine. If you want to spend the time and distribute, and distribute, and then distribute, and then distribute, and distribute, don't forget the negative, and then combine all those like terms, use something pretty nasty looking, but it would be a polynomial in this case. Do you see the polynomial? Okay, I'm not going to go that far. It'd take me 10 minutes just to distribute everything. Do you understand the idea of the product rule working with the quotient rule? Raise your hand if you feel okay with that. All right, very good.